Without further ado, let's take a look at the coding hint. Coding hints, just hints. Yeah. Don't say that that's the procedure. Just hints. I try to make that hints, and make it easier, as easy as possible for you to follow. All right. So the setup is that the virtual process running at from here to here. So these are two very big numbers. They are virtual, obviously, and the traffic is this one. Yeah. So that's you got to use the 2 gig. 2 gig is this guy, plus 1. This guy plus 1 is 2 gig, and this guy half a gig, 500 meg. And these are going to be the same for all the process you create. When you fork, when you enter the fork, the ampersand. So I've tested the phase 8. Many of you surprised why it didn't work. So I thought that your teams were doing very well. All right. So we're going to fork a process that's kind of like the parent process, but it's going to do the exec service. And then this will give us to the virtual space running. And in the virtual space, they are identical. In the beginning, they always run between 0.5 to 1.5 minus 1. Okay. Bytes. And their traffic starting address at the same traffic, VN traffic. The same VN traffic. So this is the VN start. VN end. So those are the constants for that. And of course, we need to have some kind of translation mechanism in order to do that. And that is by the piece of hardware called memory management unit. So we're going to have to create the translation table for it. Okay. So the kernel has a new data point, the OSTT. This for the OS translation table. So we're going to have a base. All virtual processes created by this command or this command. From the user proc, we are going to the virtual space. The virtual space is identical. And the OSTT translation table, the ASTT, OS translation table, we're going to call helper function get CR3 in order to obtain this. So this is in the bootstrap, okay? The bootstrap, which means that this is the OS data point we need to be initialized. And this is Speedy provided a small function assembly code. Basically, it's just assembly instructions. And then CR3 is control register 3. Okay, CR3 control register 3. That's Intel. Intel has the CR0, CR0, CR1, CR2, CR3. And this is the MMU translation table. So we're going to have this register, okay, this register set or hit we can read it, we can set it. Okay, so the opposite of get CR3 is the set CR3. CR3 given a translation table address. Okay, so a translation table address is one of the processes we have created. You can run multiple at a shell prompt. You can type fork ampersand several times and create the process as 2, 3, 4, 5, because the background running and the foreground running shell command is still there, let you enter another 4. So if one of the process has a translation table created, so this will set to one of the translation tables for that process when we load it. Okay, so we got to set CR3 before loading. Before loading the virtual space running process. We just call it virtual process. Okay? These virtual running process because they need translation tables. And each one of them has a unique translation table, so they can map the same virtual space to different actual space. Okay? So they are actually mapped to different actual space. Okay, different actual spaces. Okay, they all run in the same virtual space in terms of number, addresses, instructions, data, and so forth. They can be different code. They don't need to be the same code that we are testing. They could be child stuff 1, child stuff 2, different. But they all start from the same place virtually and end at the same place virtually. The traffic always starts at this. Okay? So these 3 things are always the same. So if they're the same, that means virtual space starting point is after popping the traffic. Okay, so the stack pointer of the CPU always start at this place to run the program, whatever that program is. And the code will always start from the end start. Okay. So this is where the VM ends. Okay. So you can see this is where the traffic is, the virtual memory traffic. So that's why this one minus this plus 1. Okay. Because we didn't point to outside, we point to inside, including this byte and this byte. So it's actually, there's 1 byte difference. The VM start from here. VM start is the instruction. We copy the instructions here. We create the traffic here. And then after popping the traffic, it's when the process runtime stack begins. Okay, so we have it set out like this. And this is 1 gigabyte in range, virtually. But when the instruction is being fetched to execute, when the stack is being read and write, the actual space is in the DRAM. DRAM by pages, page by page, that each portion of the virtual space is mapped into here. It's actually here. For the translation from the CPU addresses, actual addresses, it is done by MAU. Okay, MAU, looking at the translation table. So DRAM, wherever it has space, that can be qualified to use as the mapping target. Okay. So we're going to allocate DRAM pages and set up the virtual space running translation table, and then set the CR3, which is the register for the MAU to look at the translation table. So that's address on the first byte of the translation table. That means the address of the translation table before loading the virtual process done by the prompt loader. Okay, prompt loader, So that is the, what is this thing here? Prompt loader argument.
Traffic.
traffic frame of the process we selected to run. Which process has we selected to run? Has kernel selected to run? What's the variable name of that process? Run pit? Okay. So yeah, welcome back to 159. But in this case, what does that mean? That address, that traffic address, is the same. Again, it becomes a constant. This one. Yeah? So you no longer need to have that. Basically, they are all the same. Okay? So that's uniform. And then translation will get to the real DRAM address on the fly at runtime. Okay. So on the fly, meaning that the process running, and when process running, and the MAU, MAU translates the real address, virtual address, to real address. Okay. Then the DRAM can be accessed. Then the address is going to be known, otherwise don't know. CPU does not have the real address, only MAU. Okay. MAU has the translation and can get to the real address by looking at the translation table. Okay, we just loaded by CSC159. Okay, so this can be translated because this is very big virtual address. And there can we load the traffic. The traffic is in the page here. Traffic in the page here. It's mapped to the DRAM page, that's real. Of course. But it has to have MAU translate on the fly. Okay. So we're gonna set down the MAU and then we start to load. Then this can be translated. If you didn't set up the CR3, this would cause segmentation violation. Okay. Because I can not find that big address. Question?
So Proctor will use the VMs with virtual memory trap frame to find the trap frame that we want to run in the DRAM somewhere, and then it will run that. Well, because everything is in reference to the virtual memory's trap frame, correct?
Correct. But the translable determines which translation table you set for which processes.
So then the translation table, once it knows what it is, when Proctor runs and everything, it's going to end up at the right place, essentially, because it's the MMU is using that translation table, so that translation table goes directly to that space.
Yeah. So we have created many virtual running processes in the shell prompt. Each one of them, during the exec service, we'll have the translation table created. So this translation table goes along in the PCB for the process. So we can set a CR3 with that translation table address, and then the translation can start when the program runs. Even when start to load, it's already translated because the virtual address trap frame has got to be translated into the right place. Another process has a trap frame at a different place. Another process has a trap frame at a different place in DRAM, but virtual address is the same. Okay, so they all have the same. They all have the same virtual addresses. All right. So this is to say that each process goes to living room, go to kitchen, go to bathroom, bedroom, wherever in the house. Okay, and then in the house they appear to be the same location within that house, that virtual space, but they are actually mapped to the different actual locations, so that they all have the same virtual space construct where to start the code, but you won't fetch your other people's code. Where is the trap frame, but you won't get to other people's trap frame because the mapping into the the actual DRAM pages are different. Okay. So this is called the virtual memory extension. Okay, this is the illusion we want to make with our OS. Okay. So virtual space running process didn't really come in to be popular till the 80s. Right? Before they were real memory, real processes in the non-protected mode, real mode. And right now you have the virtual space, we have the protected mode. How are we going to protect this? Because the MAU will not translate unless the entry says allowable to translate by that process. So we can have the translation table, this one here, created for multi-processes. And the entry will indicate that this is for which process to load. Okay, so the MAU knows which process is running and translate for which process. So there's an address violation can be checked in the translation tables. The tables are also outside of the reach of the virtual running processes. So your processes, your program code cannot access them, change them, alter them. Okay, they are only created during the exec and then being used by MAU only. And the virtual space mapping is the running space of each process, and they cannot access the kernel space. Okay, so translation tables are in kernel space, and other process are in other process translation table range that your process does not translate. All right. So so this is how we can protect the processes from accessing kernel space and other process locations. So the mystery is that how are we going to build a translation table? Okay. So we have an OS translation table as the benchmark. This will also get us back after the process ends. We start from here. Your boost drive OS TT, okay, starts the boost drive memory usage mapping. Okay, so when the process ends, the virtual process ends, we reclaim the translation tables. We reclaim the DRAM pages. So we're going to switch it back. Okay, so you can see the set CR3 to A virtual running space translation table is going to come back, okay, returning. Okay, the runtime of the CPU returning to the actual space is the set CR3 to the OSTP. Okay, so here you have a virtual space running. Afterward, we have exit service, we have wait child service. These two services is going to set the CR3 back, the MAU translation table back to the original. Return to the kernel mode. Okay. Does that make sense? So we need that, okay, we need that OSTP. And we can get it by get CR3 call. We can read it, okay? We actually use the get CR3 just once in this space, okay, to initialize the OSTP. Get CR3 is used if we do have next space, that will be page fault. Okay. Page fault, okay, that's a different story. Add to PCB type. Okay, so PCB needs to have something. Like we said, each process has a translation table created. So we got to know where that translation table is. Not the whole translation table because it's big. It's used the whole 4K byte DRAM. So we're going to have the address of the translation table where the DRAM is for that translation table saved in the PCB. Okay, so we need to have additional on-site int or just an int address saving. Okay, so we can select the process and load that translation table. Okay, after we select the process, we load the process PCB. There's a TT. That address is the translation table address for that process. Because why? Because each translation table is 4K bytes. Okay. And we don't put that in the PCB, we put that in another DRAM page. So if you have 3 processes running, you will have 3 TT. The 3 TT resides in the DRAM for 3 different processes, and 3 different trap frames, and 3 different instruction pages, and other pages if you need it. Okay. So entries in the translation table point to those DRAM pages. It is one unique set of DRAM pages shared by many processes through the translation table entries to match into them. All right. So that's created during the exec service. Also, 2 alsos, expand the single page to an array of 5 to record page numbers from 5 DRAM pages. Since the virtual process will need 5 DRAM pages to start. That means that phase 9, you have 1 page number in the PCB in order to find which page is used by that process when that process exists. But now you need 5, okay? You can make a linked list if we have linked list capacity yet, okay? We don't. And then we're going to make 5 integer numbers to record the 5 page numbers, okay? 5 page numbers. So add to kernel, this is the kernel function at the end. So we're going to load virtual process. We're going to check if the TT is if the TT is null or not. If not, we just call it get CR3, set CR3 with a virtual memory. We're going to set CR3 to that process TT and call the prod loader with the virtual memory trap frame. Okay, so that is how the translation can start. All right. So if it's the is null meaning that is the old processor, the kernel processes. Okay, we call it kernel processor. We have kernel process like idle and the user. Okay, user prompt. Before we fork, is doing the child stuff is still a kernel process. It's using the OSTT. Okay, we haven't changed the TT, but now we had the fork called to make the virtual processes with the individual TTs. So we're going to know that TT is not null. Okay, other TTs are null. Okay, but the TTs are null. That's the original one. You don't need to change that. But if the TT is not null, you need to load the virtual. You need to set the CR3. Okay, CR3 before loading that process. All right. And services. Okay, services. The exit service and wait child service, when reclaiming the resources of a terminating process, the 5 DRAM pages, not 1, must also be reclaimed. Okay, so you gotta change that claiming 1 page into 5. All right, so the MAU should be informed first to change it back to OSTT, because you need to B0 them that contains the translation table currently in use. So we're gonna switch it back to the OSTT before we B0 those 5 pages. Okay, so check that you do this correctly, not just 1 page anymore, it's 5 pages. Exit service needs to create the translation table besides other things of the process. So we're gonna revisit this, we're gonna modify this basically, okay, revisit exit. And we need to allocate 5 DRAM pages, okay, 5 DRAM pages from the page queue. And then we're going to put those 5 page numbers in the PCB of that process. Okay, so basically you still allocate PCB, of course, right? You B0 the PCB, of course. And then you allocate 5 pages, meaning that you DQ the page queue 5 times to get 5 numbers put into that 5, where is that? 5 page array integer in the PCB to record that. The process use these 5-page numbers. All right, they don't need to be consecutive. You know, we enqueue the page queue in consecutive order 0 through 19. Okay, 0 through 19. So that's why we're going to get 0, 1, 2, 3, 4 for the first process, and then 5 through 9 for the second, 10 to 14, and so on and so forth. Okay. When we return 5 pages, and they're going to append to the tail. So basically, we cycle 5 pages at a time because we don't have page fault yet. If we do have next page fault, then we're only going to DQ just one at a time, one number at a time. Okay. So the whole numbers are scrambling inside the page queue, and according to whatever runtime we can.
So I think the phase before that we check if the page is invalid. I think it's -1, and then we do a kernel panic. Do we have to worry about that at all on the 5?
-1 is a previous semester concept. Okay.
Oh.
Yeah. So yeah, when you
Because that was on
where did you get that?
phase 8 or 9? 9, yeah.
Yeah.
Because it was that on the coding in on the last phase.
Oh yeah, you're
So
right.
I was
You're right.
wondering if you.
DQ return -1, then you run out of DRAM pages.
So let's say there's only three pages. So do we just kernel panic if we can't get 5, or how do you want us done?
Kernel panic. Yeah.
Okay.
That's just exception, you know. It's not very much a big deal. We're going to first learn how to say having resources, and it will work. And the -1 or not don't matter. I don't care much about it because we just increase to more pages, and then we don't have swappers, page daemon to swap out pages. So that's all the whole thing in the future phases. Can we deal with that? So right now it's just a kernel panic and return will be fine.
Okay.
You can think of I should return the page. If I didn't get 5, I got 4. I should return the 4. Don't worry about that. I don't need you to do that.
Okay.
I can handle that exception. Just display a kernel panic.
That's what page faulting is for, right? Like, if you don't get all 5 of them, then you page fault.
No, page fault is the wrong time. When the process going to rewrite somewhere that's not allocated yet.
Okay.
That causes page fault.
But we're forcing it to be allocated right now, correct? We're gonna make sure it's allocated code-wise.
Yeah, the page fault handler then will allocate a new DRAM page for data access or for code. The first code page is 4K byte, may not be enough. So when the code start to use more than 4K byte, we haven't allocated that 4K byte. That MAU will know. Okay, MAU will know. So it's kind of like this, right? The instruction is very big, more than 4K byte. But if we just start from one 4K byte, okay, 4K byte instruction space. Right now it's big enough for us. But if we have big program, then the instruction will eventually go into another 4K byte. When that happens is the EIP, okay? The traffic EIP is VM star, okay? The traffic EIP is VM star. So when the EIP increases over 4K, that becomes page fault. Because that's the virtual address need to be translated by MAU. MAU will see that the entry says invalid, okay? We got to B0 the table, DRAM pages. So by 0, that entry will be having the 0 flag and invalid. So when this single DRAM in that single page register valid, but it will go to next entry. Next entry is responsible for next 4K byte. Each entry point to one 4K byte. So that entry is 0 right now, it's all 0. So that flag will be read by MMU, knowing that the virtual address now point to this entry, but is invalid. So that calls the page fault by hardware. Okay. Kind of like division by zero. It's the same type of hardware like division by zero. That will trip the CPU to draw everything. Or like time interrupt, going to the OS, and then OS will check, and then knowing that's the page fault entry, we will push the page fault interrupt number instead of time interrupt number, and then it will jump to the IDT table to push that, and then go into the kernel. And the kernel will see the interrupt number is called page fault. We define that constant, and then it will call the page fault handler, page fault service, to recover the page fault. It may not be able to. Okay. It will try to recover the page fault by setting another DRAM page. Okay. So access service, we allocate 5 pages for the purpose of these 5 things. These 5 things abbreviated. They are the translation table. That's a main table actually. And there's a subtable called instruction table, and there's another subtable called the stack table. And there are 2 useful pages, instruction page and stack page. Basically, in phase 9, we have these 2 together in one 4K byte. We have instruction and stack running in the one squeeze the 4K byte. Okay, we put the traffic on top of 4K byte. That's where, after popping that, the stack pointer is pushed down, and then the instruction is a copy to the beginning of 4K byte. Okay, now we expand that, right? Expand this 4K byte to a virtual space, and then that virtual space 1 gig. So we have 2 4K byte pages and 3 tables, 1 main, 2 sub. All right, we build the main table. There are 6 entries to build. All right, and after we build this, save the TT pages into the PCB. Okay, PCB, and clear all entries in the TT. So it B0 this 4K byte. Okay, by number you had a macro to calculate the address, right? You use that macro to get the address, where the TT being a number. All right. So you say all these are numbers. Okay, all these are page numbers. Okay, and if you need to have 5 addresses, you probably need to define 5 different array of 5 as well for addresses. If you use the enum feature in C, your code will look nice. Enum we can let you use this label, 5 label is 0, 1, 2, 3, 4. Okay, 0, 1, 2, 3, 4. So you enum these 5 things just like the states, like the PCB states. We have an enum. You can also use that to make them in code. You mention them like this, but actually it's 0, 1, 2, 3, 4. Kind of like define 5 constants. All right, or you can basically define 5 constants. So use that as the index into array in 0 through 4. All right, so that's the meaning. But I'm just going to describe it more colloquially in the pseudocode. Okay, the last phase of the 159, hopefully that you can translate them. Yeah, so that's the translation capacity. So I don't need to feeding your exact coding procedure like enum or a constant define or macro defines. Okay, so the 6 pages, 6 entries in the main table TT. Okay, with B0, that means all the entries are zeros. All the flags are zeros. No addresses there. So we're gonna copy the first 4 entries from the OSTT to the first 4 entries of TT. Okay, so that gives us the kernel space mapping capacity. So when you have a syscall, you can locate that. Okay, you can locate a service too. Okay, kernel code, IDT. All these things need to be located. So the virtual space below has a 4 entries to map to 16 megabytes. Okay. So that's the kernel space mapped underneath. So the process runtime has the kernel space mapped here in order to get to IDT, in order to get to kernel, in order to get to service.c. Okay. So why 4 entries? Because in main table, every entry can point to a subtable that has 1024 entries, can point to 1024 4K byte entries. So one entry in the main table is responsible for 4 megabytes of space. Okay, so we need that first 4 entries from the OSTT to locate 16 meg, because the OSTT first 4 entry point to 4 subtables. Okay, first 4 entries point to 4 subtables. So OS actually has subtables too. And then that 4 subtables can point to each one 4 megabytes, because each subtable is 1K entry. Each entry can go to 4K. All right. So use the integer pointer Q to point to TT address. So this gives you a hint. Okay, you need to like put fill in the entry. You got to use a pointer and get the entry number from the first 10 bits of the number VM start. So we take the first 10 number as a number. Okay, first 10 bit as a number in the VM start. All right, and then we're going to use that as the entry number to point to the TT. Okay, point to TT, and this will happen to be 128. Okay, the first 10 bits of the VM start, which is half a key, and then that will be used as the entry number into the TT. Okay. Get the entry number from the first 10 bits of number VM starts, setting where the entry points to. Okay. And to set where the entry points to based on Q. Okay. So equals IT address. So basically, so the main table, okay, we're going to have the first 10 bit, okay, VM start as a pointer into the number of entry. 10 bit is in the range of 0 through 1023. Okay, so this one points to somewhere, and that is where we're gonna put the subtable address, okay, or hex 003, because that's the flag that we want to set. Okay, the flag is the rewrite flag and the valid, okay, present flag, present, valid, present, yeah, rewrite and present, the last two bit. We all bitwise OR into this address here, IP address. Every address has 12 zeros because they are intervals of 4K, interval of 4K. So this is 14 meg, okay. 14 meg. And then every 4K is 1 0 0 0 2 0 0 0 3 0 0 0 4 0 0 0. All right, the front don't change. And these 12 bits, or 3 hexadecimal digits, can be saved to use as flags. Okay, so these are 12 flags. So we're going to add 1 1 to the last 2 flags. So we OR 003. 003 hexadecimal is 12 binary bits. So we're going to set one entry like this. The other entry is going to be set at the VM end to accommodate the 4K byte page. Okay, so that is for the traffic subtable. So that will be the stack table address. Okay, the whole thing here. Okay, and then the flag. Okay. So the whole thing with the flag added is like this. The front 20 bits is the 20 bits is the address plus 12 zeros, 12 zeros. So sometimes pages, people say this is the page number, DRAM page number it maps to. By number meaning that 4K by portion, okay, as a number, as a DRAM page, 20 bits. And then the 12s are used as flags. 12 bits here are used flags. All right. So that's how the MAU look at it. Okay. So you say, why are we doing this? Because that's how the MAU dissect each entry. Okay. So this is how MAU interpret each entry. You won't look at 32-bit in that entry. You will look at the first 20-bit padded with 12 zeros as the beginning of a 4K byte address. To save that 12 bits, we can set flags. Okay. So altogether it's 32-bit to squeeze into 32-bit. And then we have 1024 entries. So this table can squeeze into 4K byte. Okay? All right, so we're going to build these two entries. The first 4 entries are copied from the OSTT, okay? So these 4 entries from OSTT. And this one, we're going to manually set in the ECS service. All right. All right, then we get the entry number from the second 10-bit, the first 10-bit, I'm sorry. The first 10-bit of BNN. The first 10-bit of BNN is going to give us the entry point to set this stack table address, okay, with the bit or the hex 003. Okay. So these 2 entries plus the 4 entries copied from the OSTT will make the translation table, the main translation table. But what about the instruction table and the stack table? Okay. So the instruction table is the second 10 bits of the BM star. Why is that? Because that will be the first instruction to locate. Okay, I mean you're going to translate this because the traveling EIP is set to here. So I mean you need to get the address to fetch instruction, the first instruction. Okay, and then continue from there for 4K instructions. And we have copied in. All right. So we're going to, when second 10-bit of VM star is gonna be 0. So that will be this entry here. Okay. This entry here. So the content will be the instruction page address, okay, or the hex 003. So that DRAM address has 12 zeros at the tail because it is interval of 4K. So that IP address is one of this. Okay. So basically, you can see this guy is TT, this guy is IP, this guy is SP, this guy is IP, this guy is SP. Okay. So that's the first byte address of the 5 pages. Does that make sense? But this is only for the first fork, okay? The next fork will have another set of 5 pages. They're starting from different 5 numbers. All right. So here, others are 0, okay? Others are not entry. And then the stack table, another subtable, this guy points to, okay? So this guy points to the subtable. This guy points to the the IP instruction table, okay, instruction table. And then in the instruction table, the first entry, entry 0, is going to point to the instruction page, okay, instruction page. Instruction page is where we copy the code, okay. We copy the instruction code. And then the stack page, we had a traffic. We had a traffic build here. And this is the argument. So this is going to have it in the last entry, okay. The second 10-bit, all right. The entry at 1023, because the second 10-bit in the BMTF. BMTF is very big number, close to 1.5 gig. So the second 10 bits appear to be a very big number. And then that has the address of this guy, okay? That has the address of SP or hex 003, okay? Like that. Others are all zeros, all empty. So this is the linkage of the 5 different DRAM pages. And the actual instructions here, the actual traffic is here. And that's also where the stack pointer is going to be pointing to. Okay. Stack pointer point to a virtual address, translate into the real address here. But the stack pointer does not have the real address. Okay. So the EIP has BM star. The ESP has VMTF in CPU. All right. And when you translate, and when you get the addresses from the translation main table to subtables, from subtables to the actual DRAM pages, it will give it to the cache system to see this cache hit. Cache system has the real address. Okay? Cache system is the one that receives the real address firsthand from the MNU. MNU will not tell CPU, say, you know, the real address is actually this. You were kind of dumb, you didn't know. Okay? MNU will not say that. Okay? I mean, you always get virtual addresses from CPU. CPU only care about, I'm getting virtual addresses. Okay? I'm getting virtual address to run the processes. And they are, okay, to be translated by MAU through the looking on the tables. Okay, so it ends right here. Okay, so basically it ends right here, and then this is the cache system that caching the instruction page and the stack page. Okay, the core cache, core share cache, level 1, level 2, level 3 DRAM. Okay, and then these cannot be swapped out. Okay, but that's the different story, the swapping. So these gotta be staying in the DRAM all the time. These gotta be swapped out. Okay. These are piped in through caching system in the real practice, of course. Okay, and these are cached in the MNU TLB. Okay, you remember TLB? MNU has TLB, right? What's TLB? That's the cache.
Translation look-aside buffer.
Right. Is why is it for?
When you look, it's for caching the whole lookup process through the page tables, because that involves like 2 memory reads. So you want to be caching it to avoid having to do that on every single memory access.
Yeah. Right. That's a good description. Basically, the table entries are cached here. So the tables are not being cached by the regular cache system. They are not data. Okay. They are not data. They are only cached here. Entries in translating tables are cached in TLB. Translation look-aside buffer. Basically just cache for MAU. So it has this virtual to real address mapping. So it doesn't need to retranslate. Okay, it will save a few hundred entries. It's not very big. So that most recently used page entries are inside there. Right? So it has a real address in the TLB. This is not tomato, lettuce, bacon sandwich. Okay, it's not. Is there a BLT sandwich?
Yes.
It's a TLB. So it's just a cache. So I don't know why they make such a big fuss and make it like, oh, translate to a side buffer, something really, sophisticated. Same thing with MMU. MMU is not like memory management anything. They just do a memory mapping unit. That was the original name. Okay. So this is the reason why we need to set up the translation process like this. Okay. Any question?
You said, in the coding hints, and I maybe just kind of missed this, because it said, building the first 4 entries from the OSP. Is that what all the coding hints are talking about, is building those entries? Or is there something that I'm missing here for building the entries?
You just use main CPY to copy from OSTT first 4 entry into here. Yeah. This is for one process. So the first 4 entry in the main translation table for that process need to be copied from the OSTT to map to the kernel space. All right, you know how to use GDB, right? If you, at the end, if you step through the kernel service, at the end you can print this. This is not a constant, so it's printable. This is global onside in. Global integer is fine. Doesn't need to be onside in. Yeah, it doesn't need to be onside in, it's a small number. And then you want to check the like process 2, yeah? You push N key just once, so the first fork of the process 1 created by N key is going to be process 2. But you print you can print the child PID, the PID to see which PID allocated. It could be 3, it could be 4. And then you print this, you can see the page numbers. The first 5 page numbers, or the second one from 5 through 9. And then if the reference OSTT plus 0 times 4, that means the first entry, 4 byte. Right? This is a number. This is a number. So what is right? Yeah, that's going to be still 0, although that should parentheses this. Yeah, parentheses this should be right. And then this is, because 0 is C, the same thing. I should put a parentheses here. Then you can check the 1 times 4, 2 times 4, 3 times 4. Basically, is to check the 0, 1, 2, 3, the first 4 entries, what they are. Okay, you can see what they are. So you can verify them with this. Okay, you can print the TT address, and then you can also do the same thing with this one. Okay, you dereference this with the checking. You should map the OSTT copied over, and you want to see entry 128, and then you can check the content of that entry as well. Okay, and you have to understand when a child process exec make a running virtual space, and it has the traffic very big, and the child becomes zombie. Then later on, the parent call wait will get the zombie child's exit number in the traffic, in its traffic. That number is in the EBX in its traffic, okay? Because it failed to deliver because the parent hasn't called the wait. So the child becomes zombie child. The parent now calls wait. The parent running not in virtual space. The parent runs in kernel space. So there's no translation of any big number. But the child traffic is a big number, okay? So if you have if you said, I'm going to grab child's EBX in the Weide child service code to get the exit number, at that moment, the target PC will reboot, okay? Because why? There's no way to translate that, okay? Because the child's translating table is not in use. But we want to get something from child. That's in the child traffic. In the PCB of the child traffic, the zombie child traffic, that traffic address is very big, yeah? So when the parent process, execute the Weide child service is in its own real space, cannot translate that, right? So we got to set CR3 to the child translation table to get that, and then switch it back to the running process, okay, to the OSTT. Makes sense? So that's the complication in services. We only had one, okay? Luckily, we only had one complication. But you got to consider all the processes in the real system, all right? They all run in virtual spaces. Any communication between processes through their own space, like sharing variables, they got to be done by setting a CR3 to that process in order to get a copy. The usual way is to get into the kernel space, a temporary copy, and then switch it to another process and copy over, okay? So because MAU cannot have two tables at a time. And so that also say, wait a minute, what do I invent a computer have two MMU? That's right, we're going to have two MMU, and so multi-processor can do that, okay? But a single processor, multi-cores, don't have multi-MMU. So you're going to design multi-MMU processors in the future, that each core has its own MMU. And then so that we don't need to worry about changing things between processes in virtual space. All right, does that make sense? So syscall, remember syscall always put something into the register, and the traffic, unfortunately, the address of the traffic in the PCB is a virtual space one. So everybody has their own traffic in virtual space expressions. They need to be translated in order to communicate things in the traffic, okay? So that becomes a big problem. So single mapping to the kernel space is what every process has. So every process, virtual space can get into the kernel space, but not among them, not between them, okay? Not between them. So if you have shared memory management, is to counter this problem. So the shared memory management can have their multi-processes, okay? And then have their 4K byte pages mapped to the same DRAM pages. All right, so this is the DRAM space. So one DRAM page mapped to the two virtual spaces as a 4K byte, okay? So then we can have shared memory management done, right? Right? It can be multiple, it doesn't need to be two, okay? So shared memory management is to set out a hook, and then that has the pointer point to here, typecasting to their own data structures. That's how the shared memory management does it. All right, so that's also how DLL does it, okay? DLL has dynamic link library thing, or in Unix called shared object. They are also done by one copy of DLL library or a shared object runtime library can be shared by multiple processes mapped at the bottom here as a low address mapping. Okay, so we don't need to have multiple copies of runtime code. So that can be done by the virtual space here. Okay, and the protection is done by this. Okay, so finally, you can understand how to protect security, computer security comes in. Because each entry here, the flag here, we only use these two flags. There are other flags, they are user mode, kernel mode flag. So that means that the address that entry has can only be translated given if that process is in the right mode. In a process in the kernel mode, definitely you can use it. If a process in the user mode, but the entry is set to kernel mode access only, then that will be a segmentation, but it will be a page fault as well. Okay, any flag conflict is a page fault. There are 12 flags possible, and then any one of them means a page fault. All right, so you can see this is how we can control. Say the entry is set to kernel space mapping. So that 4 entries we say map to the OSTT has the setting to kernel mode only. That flag is set, not 0, 1. Right now we got everything 0 on that bit, which is okay. We run our processes all in the kernel mode right now. Okay. So it's the whole semester is in vain. We never really get to the user mode. So we cannot get to there until this point. Okay. And then once we set this to kernel mode bit, the flags out, then your runtime in user mode, process runtime user mode cannot get into the kernel space. Okay, once it hit IDT, it will ping, IDT cannot be accessed. Okay, and then how do you set the process to run user mode? So that, say, oh, that's in the try frame. You know, the try frame can load that CS. Okay. The CS is the key in Intel processor. Other processors, they use just a flag in the kind of like E flag. You set a bit, that process traffic loaded and becomes user mode or becomes kernel mode. Okay, and the user mode go to kernel mode requires interrupt INT. Only call interrupt, and then you will change mode. Once you change mode, you can get IDT. You can go to the kernel space to execute kernel code. If the kernel code is not hacked, then that's benign code. That's okay. Okay, you cannot INT and come back to execute user mode. You will return back to the user mode when the IRET will return the E flags that has the mode, user mode come back. Interrupt will go into kernel mode. Make sense? Yeah? But in Intel processor, they put into the CS, not the E flags. And then that in the last 2 bits. Okay, it's a 16-bit register actually. And then the last 2 bit is the mode. So 00 is kernel mode, 11 is user mode. Here is between. And then Windows use it to do the syscall, the library call. So Windows has 4 modes from user mode, going to library call, like when you print hello world. And then further going to syscall when you hello world print becomes a write. Okay, and then get into the kernel, and then that will do the process scheduling, etc. And that's the loader and all the things that are in the kernel mode. So it has actually 4 level can be set in the Intel code segment selector. These 2. Okay. If we load the CS with 11, then your process idle, user prod, child stuff all running in the CS last 2-bit 11 in user mode. And then therefore it has to do the interrupt call to change the mode to go into the kernel space because MAU will see that mode. MAU will check the CS mode. Okay, where's MAU? So MAU will check that mode, okay, and then see the entry requires what, okay, in the flags. All right, so what about other flags? All right, just give me 1 more minute. I have the writing here. You can take a look at the flags. There are 7 flags that are useful, that are meaningful. We're not doing these, okay? We just do the first 2 flags. So user mode cache policy, we can actually set cache policy about the page it points to use cache or not. And then the access bit, 30-bit. So that if the data page has been changed, then we need to swap swap space. Okay. So extension of the DRAM pages is the swap space. You see many entries are used in the tables, and then the instruction in that page gets more and more. And then we have a swap space like terabytes. So that's the swap partition to swap in, swap out. Okay. The LRU, the least recently used the DRAM pages can be swapped out. That's done by page daemon, periodically, to maintain the DRAM have a healthy proportion of used pages. Okay, so LRU can be found by access bit. Whenever MAU access this entry, it will set this to 1, okay? When you look at this entry. So periodically, like time interrupt could be a good candidate. Like time interrupt, we can check the translation table currently in use, how many entries are accessed since the last time we look at, okay? So we can approximate the LRU by adding a count into each page, the LRU count, okay? So we can set the LRU count and say, you have LRU count, how many pages, 1 megabyte page. So that is going to be an integer count that we can count according to what page that this one is, the page number, okay? So this is the page number, from 0 to very big. So that is going to give us the count, initially 0, and then we can up count. We can set it to 0 once it's accessed. When it's not accessed, we can increment it by 1. So we have the aging number here that can be selected. Whoever pages that has the largest number can be swapped out to the disk. And when it's dirty, it's got to be swapped out too when we have replacement policy, like your caching system. And we swap in also can be indicated, which has extra space we can designate as a swap out. The entry says it's not there, not present, but another flag set is in the swap. When we swap out, we set an entry, a mark that indicates, it's not brand new, it's old, it's swap out, so we can swap that in. All right, so you can, if you can link all these things together, from this space, then you can start to understand more and more about the OS operation. But unfortunately, the semester ends, so the party, get started, then we end it. Anticlimactic.
Just enough to be dangerous.
Right. What's that?
Just enough to be dangerous.
Yeah, just enough to be dangerous. Yeah, thank God.